Simulation is an essential part of any capacity or service planning project. Although simulation is essential to these efforts, the meaning and application of simulation is generally misunderstood. In general, simulation means imitation or enactment. Simulation may be a physical simulation such as this horse simulator. It could be a procedural simulation such as a combat simulation, which could be conducted by individuals pointing sticks and yelling bang or firing weapons with blank rounds. It might also be a mathematical simulation in which a future state is calculated. Simulation is a means of measuring the effects of something that has not actually happened. Railroad operation simulation is typically a mathematical model, although model railroads have been used for the purpose. A mathematical model does not require a computer, although a complex simulation is certainly made practical by a computer. The essential elements of rail infrastructure and operations planning are time and distance. The mathematical model projects the distance a train will travel over time. The distance is used to determine the infrastructure configuration at that point. The simulation may involve only one train, in which case the purpose of the work is to determine the performance such as speed, energy consumption, emissions, or other factors of the train, or particularly the locomotive. The simulation may involve several trains, in which case the purpose of the work is to determine the relation of the trains to each other and to the infrastructure over time. In the former case, the train speed is repeatedly calculated using a formula which uses the sum of all propulsive forces, such as the locomotive, gravity, and momentum, and all resistive forces, such as braking, friction, air, and gravity. This is a labor-intensive procedure that is most conveniently done with a computer program. Typically, the calculation is conducted at 1-second intervals in the model time. In real time, there are many of those calculations performed per second. In the latter case, the running time between stations may be the result of observation or the result of calculation. However, the train simulation may be conducted manually using the computer-calculated times. The running times can be incorporated from a spreadsheet calculation of the movement of a train, which can be plotted as a time-distance graph manually or by the spreadsheet program. After the string line diagram has been developed, the relationship of the trains to the infrastructure and to each other can be examined. If the purpose of the work is crew management, equipment management, or an approximation of a timetable, the simple time-distance level of detail is sufficient. If the purpose of the work involves scheduling over a route that has infrastructure constraint on the free movement of trains or examination of the adequacy of the infrastructure for the traffic, the distance calculation must represent the specific track elements occupied by the train, rather than just the distance the train has traveled. This level of detail is beyond that easily drawn on a string line diagram by hand. Simulation in the rail infrastructure and operations planning context generally means rail operations simulation computer software. Simulation software is typically complex and comprehensive. Trains, infrastructure, and some rules of train movement are the input data. A traffic or string line diagram and an array of statistical data are the typical outputs. The need for complexity of simulation software is determined by the complexity of the research and the accuracy required of the output. Although simulation software is a commonplace part of railroad infrastructure design and service planning, the capabilities and uses of simulation are not well understood. Simulation software and a chainsaw are similar. Both are tools. Neither can perform the intended function by itself. Both facilitate work that can be done another way. Both can produce undesirable results if used improperly. Both can be beneficial under the control of a skilled professional. Both can be dangerous in the hands of someone who is not. Complete simulation software packages combine all of the stages, develop the running times, calculate the locations of the trains over time, including specific track elements occupied by the train, and produce reports about train movement and infrastructure usage. Simulation software packages include a train dispatching model which resolves conflicts. meaning more than one train trying to use the same segment of track simultaneously. Simulation software packages generate a stringline diagram and several reports about what occurred during the simulation. Sometimes the reports are quite specific about train interaction and infrastructure use. The reports may, however, be summary reports providing delay statistics such as train delay per 100 miles, fuel statistics such as fuel use throughout the simulation, and the amount of time that trains were moving as opposed to the amount of times that they were not. Simulation software provides a wealth of information. It does not, however, answer questions, such as what can be done to eliminate congestion at this station or what needs to be done to reduce or eliminate delays. When the simulation is used for research into the best infrastructure arrangement or the best service plan, the methodology is heuristic, essentially trial and error. The researcher may try infrastructure arrangements and or train schedules on a hunch or a guess in an effort to reduce a statistical measurement such as train delay. However, the most productive use of simulation involves developing scenarios using principles of timetabling and capacity, then testing the results with simulation. In North America, simulations generally represent several consecutive days of operation. Randomized represent the standard random operation of North American railroads. Random operation is inherently flawed. Simulating many days of random operation and analyzing the statistical output for the entire period may be misleading. A more effective procedure is to work with a single day of the heaviest traffic that is anticipated. This method is more effective if random operation is minimized, but developing a solution for a single heavy day is more effective than trying to develop a solution that applies to a period of several days of random operation. Best practice is to examine the stringline output for information that can lead to an exact conclusion. Once that is acceptable, the summary statistics may be useful.